All right, in this video, we're going to evaluate integrals using the substitution rule. Okay, so let's get started. The idea is we want to make a substitution with a new variable for some expression within the function, not the entire function, so that when we take the derivative of that variable, and with that derivative we find the corresponding differential, the resulting differential can be used to replace the remainder of the x terms, including the dx, that weren't replaced by the initial substitution. So what you notice here is that the derivative of 1 minus x squared is something with an x to the first. And outside of this 1 minus x squared, not thinking about the dx at the moment, we have just an x to the first. So we can make the substitution u is equal to 1 minus x squared. All right, so that gets rid of this entire term under the integral. Okay, so now we want to find the corresponding differential du. To do that, we say du dx is what? So what's the derivative of 1 minus x squared? It's minus 2x. Okay, so now we're dealing with differentials here, so we can, we talked about this in the previous video. We can think about the idea of multiplying, both sides of the equation by a differential. So the idea is we just don't want to think about, the book is telling us don't think about this idea of finding du and replacing dx with du. Don't think about that as like you're dealing with the actual infinitesimals that are associated with the derivative process. But okay, the differential du, if we multiply this entire equation by dx, du is minus 2x dx. Okay, but what do we have inside of the integral? Outside, we substituted 1 minus x squared for u, and what's left? And we have an x and a dx. Okay, but this is minus 2x dx. So if we divide both sides by minus 2, we get now there's the x dx. Minus 1/2 du is equal to x dx. Now we can make the substitutions. Okay, so what we have is, 1 minus x squared, that's the square root of u. Okay, and then x dx is minus 1/2 du. Okay, so now let's bring this minus 1/2 out front of the integral. And there we go. So now the substitution has simplified the integral to something that we can work with. We know how to find, this is a basic integral that we found in the previous section. We can use the power rule for integration. So this is u to the 1/2 plus 1 over 1/2 plus 1. Okay, so we've got minus 1/3 u to the 3/2 plus c. Okay, but now we just need to substitute the u back in here. So what we have is and that is the answer. Okay, and so just remember, we found the kind of all by itself, we found the capital F of u. All terms, a full expression, it could be a sum of terms, of two or more terms that all have u's, all have the variable. And then then separate from that, we just added the plus c. Okay, so again, whenever you do the antiderivative, you've got the variable term or terms, so it could be a sum of multiple terms, but every single term has the variable in it. That's the capital F of the variable. And then once you have that capital F of the variable, you kind of put that in its own box to the side, and then you just put a plus c at the back end to make it fully general. Right? So like you don't want to get confused and start putting plus c's next to the variable in here. No, there's going to be this one capital F of the variable by itself. It's some expression with one or multiple terms added together, or two or more, or one term, multiple terms added together they all have the variable. There's no constant terms, to where and that capital F of u is such that if you take f prime of the variable, you get the function in the integral. Once you have that, then you just add a plus c to the back end. Okay, so let's substitute. U is equal to, this is pi over 2t. Okay, so we can replace what's inside here, and then if we do du dt, we get just pi over 2, so that we can find the differential du, which is equal to pi over 2 dt. Therefore, but we have, all we have is a d1 times dt. So we want to solve for 1 times dt. That's going to be 2 over pi du is equal to dt. Okay, so what we have is, making the substitutions, cosine of u times 2 over pi dt. So we can bring out the 2 over pi. Oh, no, this is du. 2 over pi du. We can bring out the 2 over pi. So cosine of u du. There we go. So this is equal to 2 over pi sine of u plus c. Okay, but u is pi over 2t, so, or pi t over 2. There we go. Okay, so again, the idea is you want to make a substitution to where you have u is equal to something, but then the corresponding differential, the du, winds up being something within the integral. So I see a sine theta d theta, but there's also the potential to do a cosine theta d theta. But okay, if we say u is equal to cosine theta, all right, so then in that case du d theta is equal to sine theta, or minus sine theta. And so du is equal to minus sine theta d theta. Okay, so minus du is equal to sine theta d theta. Now we can make the substitutions, and so you got u cubed times minus du. There we go. So this is, using the inverse power rule, u to the 4th over 4. Okay, now substituting the u back in, you've got minus 1/4 cosine to the 4th theta plus c. Okay, so the idea is, again, we want to substitute for something that, so that when we take that, the derivative of that something, the result is something else in the integral. And so if we take the derivative of this here, we'll end up with something a, because the x will go away, and then something x squared, because this will go down by 1 power, and that's kind of the form here. So let's do u is equal to 3ax plus, okay, so du dx is equal to 3a plus 3bx squared. So we've got okay, so we want to make, we're looking for a plus bx squared dx, so we can factor out a 3 here and then divide both sides by 3. So 1/3 du is equal to a plus bx squared dx. And there we go. This is a plus bx squared dx. So this integral is square root of u and then 1/3 du. So you've got u to the minus 1/2 du. Okay, so inverse power rule, minus 1/2 plus 1 is 1/2. Okay, so we've got 2/3 root u. Now we substitute the u back in, and we've got there we go. All right, so I see secant squared theta and tangent theta, and so what immediately comes to mind is the fact that the derivative of tangent theta is secant squared theta. So let's do u is equal to tangent theta. So du d theta is equal to secant squared theta. Okay. So du is equal to secant squared theta d theta. Okay, so there we go. So making the substitution, we've got tangent, so u cubed du. Pretty cool, right? So this is u to the 4th over 4 plus c. So this is, we got 1/4 tangent to the 4th theta plus c. All right, so here we, if we had to, we could expand this out into, it'd be a bunch of separate terms, and it would take a while, but we could do it. But let's obviously consider substitution. And so looking at this derivative, if we take the derivative of x cubed plus 3x, we're going to get the same order as this. It'll be a second order term and a 0 order term. So, and we're not going to worry about the constants. The constants you can always factor out. So u is equal to, let's do x cubed plus 3x. Okay. So du dx is equal to 3x squared plus 3. Okay. So du is equal to 3x squared. Okay, yeah. So we can factor out the 3x squared. Okay, so yeah, divide both sides by 3. And we've got and there you go. There's the x squared plus 1 dx, right? And then here's the u is x cubed plus 3x. So making the substitution, we've got u to the fourth, and then times 1/3 du. So 1/3 u to the fourth du. So this is 1/3 u to the fifth over 5 plus c. So 1/15 u to the fifth. Okay, and so now if we substitute this in, we've got like that. There we go. Okay. Here, so I want to say the derivative of arc tangent of x is like 1 over x squared plus 1. So arc tangent x. Yeah. Okay, so if we make u equal to then du dx is equal to, and so we've got du is equal to, and so there we go. Now we can make the substitution. So what we've got is u squared du, just like that. So this is 1/3 u cubed plus c. So this is 1/3 arc tangent x cubed plus c. Okay, what is the derivative of cosecant? Okay, what about cotangent? There we go. Okay, so the derivative of cotangent x is minus cosecant squared of x. So if we say u is equal to cotangent x, then du dx is equal to minus cosecant squared of x. So du is equal to minus cosecant squared of x dx. Okay, so minus du is equal to cosecant squared of x dx, and that's what we're going to substitute for. So now we've got root u and then minus du. So minus u to the 1/2 du. We've got minus u to the 3/2 over 3/2 plus c. So this is minus 2/3 u to the 3/2 plus c. So this is minus 2/3 cotangent of x to the 3/2 plus c. Okay, so here, like we can't say 1 minus cosine squared theta is sine squared theta, but this is 1 plus cosine squared theta. I don't think there's any trig identities that could help us here in the denominator. But let's think about doing, what is sine of 2x? That's 2 sine x cosine x. Okay. All right. Now, okay, yeah, what if we made u equal to cosine squared x? Then du dx would be what? 2 cosine x times the derivative of cosine x, which is sine of x. So minus 2, and then I could put sine x first, sine x, cosine x. Yeah, that should work. Okay, so dx, and then we've got, so we'd have minus 1/2 du is equal to sine x cosine x. Well, no, we don't want to do that. It would just be, no, we would say minus du is equal to 2 sine x cosine x. So, okay, we make the substitution, and we've got 1 plus u, not u squared, just because u is cosine squared, and then minus du. Okay, so now we need to, so this is, okay, so we need to make another substitution. Z is 1 plus u, so dz is du, because dz du is just 1. So in that case, we've got 1 over z dz. Okay? Now this we know is the natural log of the absolute value of z, which is the natural log of the absolute value of 1 plus u. Okay? And now, which is the natural log of the absolute value of 1 plus cosine squared of x. But, okay, wait, I need to do the plus c. So, okay, this would be plus c here, right? This is the full capital F of the variable. Now add plus c to the back end. Plus c to the back end, plus c to the back end. So this is natural log of the absolute value of 1 plus cosine squared of x plus c. And wait, I forgot the minus sign here. So this is that minus sign there, minus sign there. So the minus sign comes here. So we have a minus sign. Okay, so what is the, let's see, the derivative of inverse sine. There you go. So we can say that u is equal to inverse sine of x, du dx is equal to its, okay, so du I can put it up here. Okay, so making the substitution, we've got 1 over u du. Natural log of the absolute value of u. So this is natural log of the absolute value of inverse sine of x. Well, yeah, and then plus c. Okay, so if you take the derivative of 2x plus 5, you don't get something of the order 1. So this is a tougher problem. Let's see. Well, let's just see what happens when we do u is equal to 2x plus 5. I'm curious. So du is equal to 2 dx. Okay, so what we get is x u to the 8th times 1/2 du. X u to the 8th. Okay. So what is x then? So we can solve for x here. U minus 5 divided by 2. And so if we plug that in, 1/2 u minus 5 divided by 2 times u to the 8th du. And this should simplify because it gets rid of this 2x plus 5 all under the 8th power. So we've got u to the 9th minus 5u to the 8th. Okay, so this is 1/2, and then you'll have u to the 9th divided by 2 minus, or du, minus 5/2 u to the 8th divided by 2 du. Oh no, it would just be u to the 8th du. All right, so it's 1/4 u to the 9th du minus 5/8 u to the 8th du. Okay, there we go. So 1/4 u to the 10th over 10 minus 5/2 u to the 9th over 9 plus c. So this is 1/40 u to the 10 minus 5/18 u to the 9th plus c. So 1/40, 2x plus 5 to the 10th, minus 5/18, 2x plus 5 to the 9th, plus c. That's the answer. And actually, I missed something here, so I forgot this one. There should be this should be 4. I forgot to apply this 1/2 factor here. So this is 4, this is 4, and so 9 times 4 is 36.